Hello guys, welcome back to my channel, and in this video I would like to explain the concept of implicit differentiation. Now, as you might know, this is because I have restarted with my high school calculus playlist. So in case you haven't seen my previous videos about derivatives and how to calculate them, I I have probably added a card up there somewhere. So just click on that and go to my previous videos. But for you other people who have seen my previous video, let's go ahead with implicit differentiation. Now in the previous video we had y equals some expression in x, right? Say inverse sine of x plus square root of 1 minus x squared, for example. So it was always an expression of x, right? And y was separated, so we could directly differentiate both sides. And we ended up with some expression in x. So that was our dy by dx, right? But now we are going to have a function, an expression rather, not even a function. We are going to have an expression where we cannot separate y like this. We can't make y the subject. So we can't make y the subject of the equation. So to give you an example of that, we have, say for example, y squared plus the sine of y being equal to x plus e raised to x minus cosine of x. Now because of this addition between these y terms, we can't separate a single y out, right? And even if we could, it would be really hard and not worth our time. So what do we do now? How do we find dy by dx? In these type of questions, they tell you to find dy by dx. So at the end of differentiation, you make dy by dx the subject of the equation, and you get a certain expression. So you'll see that in a while. So how will we differentiate this? Well, the differentiation was with respect to x, right? And we have a y. So why don't we try to use the chain rule? Because that's the best bet we have. Why don't we treat y like an inside function? Same here, right? Y can be treated as an inside function. I mean, when we had forms like sine of root x, what did we do? We used the chain rule, right? When we differentiated this with respect to x, we obtained cosine of the inside function as it is times the derivative of the inside function. Now instead of this root of x, we have a y term. So how will we differentiate this? We'll again use the chain rule, right? So cosine of inside function as it is, y, times the derivative of y with respect to x. Well, in this case we had our square root of x differentiated with respect to x. We could go ahead and differentiate this because we know the derivative of this to be cosine of square root of x as it is divided by 2 times square root of x, because that's the derivative of root of x. But in this case we don't know what's the derivative of y, right? Because we don't know the derivative of y because we don't have enough information, right? So we just keep this as it is. So applying chain rule now, we have the derivative of y squared plus the derivative of sine of y being equal to the derivative of x plus d over dx of e raised to x minus d over dx of cosine of x. So as I said, we just use the chain rule now. So what's the derivative of the square function? It's 2 times whatever was the argument, right? Here the argument is y, so 2 times y, but we still have to differentiate the inner function. What's the inner function? Y. So dy, so y differentiated with respect to x is dy by dx. Now we do the same thing here. What's the derivative of the outer function? Cosine of keeping the inner function intact times the derivative of the inner function, so dy by dx is equal to x differentiated with respect to x will give us 1, and e raised to x is just e raised to x. Negative cosine will be a positive sine of x. In the x part there is no problem because we just have x as the central argument, so we don't need to include any dy by dx terms. So if you want to think about, if you don't want to think about differentiating a function of y with respect to x as using the chain rule, you can use the analogy that it's basically differentiating with respect to y and then multiplying by dy by dx. You can think about it that way also. That's because you can write the d over dx as d over dy times dy over dx. So this d over dy is basically acting on the y squared. That will give us 2y times this dy over dx. So that's an interesting analogy that works all the time. So you may want to use that. You can use that. So as I said, we have had to find dy over dx. So let's just factorize the dy over dx from these terms. So we have 2y plus the cosine of y being equal to 1 plus e raised to x plus sine x. Now just to make dy over dx the subject of the equation, we divide everything by this sum of y functions. So we obtain 1 plus e raised to x plus sine x divided by 2y plus cosine of y. So that's what we do when they tell us to find dy over dx. We make dy over dx, factorize it out, make it the subject of the equation, and then just divide both the sides by any remaining terms of y that are not part of the dy over dx that we wanted to make this equation the subject of. So let's do some examples that will hopefully clarify stuff for you. So now they're telling us to find dy over dx when we have sine squared y plus cosine of x times y inside the argument being equal to pi. So as I said, let's differentiate both sides with respect to x. So we have derivative of sine squared y plus derivative of cosine of x times y being equal to the derivative of pi. Pi is a constant, the derivative of a constant is 0. This goes to 0. Well, now we can simply use the chain rule. So we have 2 times the sine of y times the derivative of the sine of y will be cosine of y times the derivative of y, which is dy over dx. I hope you know how to use the chain rule. I'm not going to show all the steps. Okay, now time to use chain rule again. So we have derivative of cosine is negative sine times the inside argument as it is times the derivative of x times y being equal to 0. Well, this is straightforward. 2 times sine of y times the cosine of y is nothing but the sine of 2y times dy by dx minus the sine of x times y, and looks like we are going to have to use the product rule here. So we have x times dy over dx plus y times the derivative of x, which is 1, so just y over here, being equal to 0. Why don't we take the negative sine xy times whatever, basically this term on the right hand side. So we have sine of 2y times dy over dx being equal to, now I'm going to expand the bracket, so sine of xy, x times sine of xy times dy over dx plus y times sine of xy. Now I want to take the dy over dx term on that side and factorize the dy over dx. So we have sine of 2y minus x times the sine of xy being equal to y times the sine of x times y. Well, now divide everything by what's multiplied alongside with the dy over dx term. So we get y times the sine of xy divided by sine of 2y minus x times the sine of xy. So that's basically our dy over dx that they required us to find. Now let's do a nice one. So we have y being equal to square root of cosine of x plus the square root of cosine of x plus the square root of cosine of x. But the thing is, this is like a nested radical that we have. So cosine plus root of cosine plus root of cosine, and this process sort of goes on till infinity. So what are we going to do? Well, we can do one thing. We can square both sides and get rid of this external root that we have, this first large radical that we have. So we have y squared being equal to cosine of x plus square root of cosine of x plus square root of cosine of x plus square root of cosine of x ad infinitum. So this goes on till infinity again, because if you just take out one term from infinity, it doesn't matter to infinity. So we have y squared being equal to, now recognize that this thing is just our y again, right? As I said, you just remove one of the radicals from an infinitely nested radical, it doesn't matter to that, right? It doesn't change that. So we have cosine of x plus y. So the interesting part is what did not seem like like a case of implicit differentiation, because in the start it was actually evident that y is the subject of the equation. You could have simply started differentiating, but that would have been really bad, because there's an infinite radical that you can't surmount. So just using some clever tricks and clever manipulations, we now have converted this into an implicit form. So now let's differentiate with respect to x. This is really easy to differentiate now. So we have, if you differentiate this, you have 2y times dy over dx being equal to negative sine x plus the derivative of y with respect to x is nothing but dy over dx. Let's make that the subject of the equation. We have dy over dx times 2y minus 1 being equal to negative sine x. This implies that dy over dx is nothing but sine x, and we can switch the order of 2y minus 1 because if we suck up this negative in the denominator, so we have 1 minus 2y. So that's basically our dy over dx. It's quite unexpected, I know, but that's how math is. Okay, let's do a proving question now. So we have the secant of x plus y divided by x minus y being equal to a constant a. We need to prove that dy over dx is going to be y over x. So we need to prove this. So, well, having a secant on the other side would make more sense. Rather, it will convert into a secant inverse. So we have x plus y divided by x minus y being equal to the secant inverse of a. Now we can actually consider differentiation. So now when we differentiate with respect to x, we just have to use the quotient rule, it seems, right? Because it's a fraction, x plus y divided by x minus y, and then we have the derivative of the secant inverse of a. Well, a is a constant, the secant inverse of a is again a constant, so the derivative of a constant is 0. Nice. Now we have to use the quotient rule, as I said. So we make the denominator function weight as we differentiate the numerator function, minus we make the numerator weight now and differentiate the denominator with respect to x, obviously, divided by don't forget to divide by the square of the denominator, so x minus y, but the whole thing squared is going to equal 0. So now you can cross multiply the denominator to the right hand side and you can get rid of that. So you now have x minus, only the numerators left, so we have x minus y times, we can differentiate this, derivative of x is 1, derivative of y is dy by dx, minus x plus y, derivative of x is 1, minus derivative of y is dy over dx, being equal to 0. Let's just expand the brackets. We have x plus x times dy over dx minus y times dy over dx minus x plus minus minus will make a plus x times dy over dx. We have a minus y, minus minus will make a plus y times dy over dx being equal to 0, and looks like many terms are going to cancel out here, terms like these. So we are left with 2x times dy over dx. We can take the y terms on the other side, the negative will turn to positive, so 2y, cancel out the 2's. This implies that dy over dx is nothing but y over x. We just divide everything by x. So hence proved. This was a really nice one, you have to admit it. Okay, now we have a harder example. So if we have square root of 1 minus x to the 2nth power plus the square root of 1 minus y to the 2nth power being equal to a, which is definitely a constant, times x to the n minus y to the n. We have to prove that x to the n minus 1 times the square root of 1 minus y to the 2n divided by y to the n minus 1 times the square root of 1 minus x to the 2n the derivative of x is going to be this crazy expression. We need to prove this. Derivative of y with respect to x, sorry, is going to be this crazy expression. So we essentially have to prove this. Now how do we start? I would first like to rewrite this in a different way. So we have, instead of x to the 2n, I can write this x to the n, but the whole thing squared, right? Plus I can write this as 1 minus y to the n, but that's squared. You know, we can just use property of exponent and multiply the powers like that. So we'll end up with 2n again. So you know, equality is maintained. So we have a times x to the n minus y to the n. Now look at the left hand side. If you remember yesterday's video, you might think that this calls for a standard substitution. If you remember our standard substitutions, we are going to let x to the n equal sine of theta, and y to the n we'll have to take another different angle because x and y are different. We are going to let y to the n equal, say, sine of alpha, and you'll see how that's going to help us. So with 1 minus x to the n is sine theta, so sine squared theta plus square root of 1 minus sine squared alpha being equal to a times what's x to the n sine of theta minus sine of alpha. This is going to be 1 minus sine squared theta is cosine squared theta under a root. So you lose both the square and the root to just get cosine of theta, plus you have a cosine alpha here similarly, and we have a times sine of theta minus sine of alpha as it is. Now I want to use some trigonometric identities. Say if we had cosine of A plus cosine of B, that can be written as 2 times cosine of A plus B divided by 2 times cosine of A minus B divided by 2. And if we had sine of A minus sine of B, that would be 2 times cosine of A plus B upon 2 times the sine of, here the order is important, A minus B upon 2. So we are going to use these two identities on the left hand side and the right hand side. So now we end up with, you know, we can just use formula number 1 here to end up with 2 times cosine of alpha theta plus alpha, sorry, divided by 2 times the cosine of theta minus alpha divided by 2 being equal to 2a times the cosine of theta plus alpha divided by 2 times the sine of theta minus alpha divided by 2. 2's will cancel out. So will these cosine of theta plus alpha divided by 2 terms. So all we are going to left with is cosine of theta minus alpha by 2 being equal to a times sine of theta minus alpha by 2. So we can take the sine on the other side in the form of a division. So we have cosine of this angle divided by the sine of the same angle, which will be the cotangent of that angle, which is theta minus alpha by 2 being equal to a. Now why don't we take cot inverse on both sides? So we have theta minus alpha divided by 2 now outside of the cotangent, because we have a cot inverse of a on this side. We can take the 2 on the other side also. We have theta minus alpha being equal to 2 times cot inverse of a. Now what's theta and what's alpha? Remember our substitution. So theta will just be sine inverse of x to the n, and alpha will be sine inverse of y to the n. We can just directly use this substitution now. So this will be sine inverse of x to the n minus sine inverse of y to the n being equal to 2 times the cotangent, inverse cotangent of a. Now finally, after doing all these manipulations, we are ready to differentiate. So finally we differentiate with respect to x. So we end up with the derivative of this thing, which is going to be 1 divided by square root of 1 minus x to the 2n, because it's x n the whole thing squared, so x to the 2n, it becomes x to the 2n, times the derivative of x to the n by the chain rule, don't forget the chain rule, minus the derivative of this thing is going to be 1 over square root of 1 minus y to the 2n similarly, times the derivative of y to the n, chain rule again, derivative of, well, a was a constant, inverse cotangent of a is a constant, multiply 2 to the constant, you have another constant, so this is going to be 0. I repeat, the derivative of a constant is 0. So now time to differentiate this using the power rule. We have n times x to the n minus 1 divided by the square root of 1 minus x to the 2n being equal to, now I'm taking this on the right hand side. We have the derivative of y to the n using the power rule. We have n times y to the n minus 1 divided by the denominator as it is 1 minus y to the 2n, but don't forget the dy over dx, because it was differentiation with respect to y, chain rule, we have a dy over dx. Now the n's will cancel out and we can make dy over dx the subject of the equation. So we have the square root of 1 minus y to the 2n times x to the n minus 1 divided by square root of 1 minus x to the 2n times y to the n minus 1, and all this is just equal to dy over dx, and that's exactly what we had to prove, right? Let's just go up above and check that if we are correct. So yes, that's exactly what we had to prove. So we can say hence proved. That's the end of it. I mean, I thought you'd like this relatively challenging question, so I put this in this video. Now let's have some fun with logs and exponential functions. So we have e raised to y minus x being equal to the natural log of y divided by x, and we have to find dy over dx. as you might have guessed. So let's just differentiate everything with respect to x. So we have a d over dx e raised to x minus y being equal to d over dx of the natural. I can write natural log of a divided by b as natural log of a minus the natural log of b. So we have natural log of x minus natural log of y. Well, using the chain rule, e raised to y minus x times the derivative of x minus y being equal to 1 over x, that's the derivative of the natural log, minus 1 over y times dy over dx. Implicit differentiation, we just learned that today. So we have e raised to x minus y times 1 minus dy over dx being equal to 1 minus x 1 over x minus 1 over y times dy over dx. Now if we were to quickly make dy over dx the subject of our equation doing some basic algebraic manipulation, we end up with e raised to x minus y minus 1 over x divided by e raised to x minus y minus 1 over y. So great, we found our dy over dx. Now let's do another proof. We have y times the natural log of x being equal to y x minus y, and they're telling us to prove that dy over dx is going to be the natural log of x divided by 1 plus the natural log of x, but the whole thing squared. So now let's just differentiate this with respect to x. There's nothing we can possibly do over here. So we have to use the product rule. We have y times the derivative of the natural log of x minus natural log of x times dy over dx being equal to 1 minus dy over dx. Derivative of the natural log of x is 1 over x. So we have y over x minus natural log of x times dy over dx being equal to 1 minus dy over dx. And just doing some basic algebra, we have dy over dx is equal to 1 minus y over x divided by 1 plus natural log of x. Well, notice that whatever we had to prove, there was no y, so we need to somehow get rid of this y. And how are we going to do that? By using the question that we have started with. So let's try to isolate our y over x. So we have basically, we can take this on the other side. We have y equals x minus y times the natural log of x. Divide everything by x now. Y over x is equal to 1 minus y over x times the natural log of x. What we can still do is make y over x as the subject of the equation. So we have y over x times 1 plus this ln of x taken on the other side is equal to 1. So y over x y over x is going to be 1 over 1 plus the natural log of x. So let's plug that value over here in our dy over dx equality. We have 1 minus 1 over 1 plus natural log of x divided by 1 plus the natural log of x. That becomes 1 plus natural log of x minus 1 divided by, we have two of these 1 plus natural log of x's, so square that, we lose the ones. We have the natural log of x divided by 1 plus natural log of x, the whole thing squared. And that's what we had to prove. So hence proved. So now we have y equals log of sine x, but it's a log to the base of cosine of x. So what are we going to do now? Remember our base changing formula. So say we had log to the base a of b, you can write this to another base log c, log of b to the base c divided by log of a to the base c. So what's in the base is in the denominator when we change the base. So we know natural logs only, right? We know the derivatives and stuff of natural logs only, right? So natural log is log to the base e. So let's make that change. Let's change the base to e. So we have the natural log of sine of x divided by the natural log of cosine of x. Well, now we are ready to differentiate. So we can differentiate with respect to x proudly. We get dy over dx. We have to use the quotient rule. So natural log of cosine of x times the derivative of natural log of sine of x minus natural log of sine of x times the derivative of the natural log of cosine of x, but divided by natural log of cosine of x, but the whole thing squared. So we have dy over dx, that's going to be natural log of cosine of x. This is going to be cosine of x divided by sine of x, or cotangent of x, and derivative of the natural log of cosine is going to be negative sine of x divided by cosine of x, or negative tan of x. That negative and this negative will make a plus natural log of sine of x times the tangent of x divided by, we can write this as natural log squared of cosine of x. So that's what we do when we have a different base and not e. We use the base changing formula and then differentiate normally. So what if we have now y equals x times square root of x squared plus 1 divided by x plus 1 to the 2/3 power. Well, if you say that we have to use the quotient rule, well, good luck on doing that on your own. I mean, it's really hard, and it's gonna take a lot of time. So might I advise something? Take natural log on both sides. When we do that, we have natural log of y being equal to natural log of x times x square root of x squared plus 1 divided by x plus 1 raised to the 2/3 power. And what good did that do us? Because now we can split this into, using log properties, natural log of x plus the natural log of square root of x squared plus 1 minus the natural log of x plus 1, but to the 2/3 power. So now we have natural log of y. We can still simplify this. Natural log of x as it is. We can bring the half. The square root is a power of half. We can bring the power down. Half of the natural log of x squared plus 1. Same thing over here. Minus 2/3 the natural log of x plus 1. And now is a great time to differentiate with respect to x, so that we have implicit differentiation. 1 over y times dy over dx is equal to 1 over x plus half of 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 2 by 3 times 1 over x plus 1. The derivative of x plus 1 is 1, so no change in the numerator. So these twos are going to cancel out. So we have dy over dx. We can take the y on that side. Y times 1 over x plus 1 over x squared plus 1 minus 2/3 of 1 over x plus 1. But we can actually make a substitution for y. What's y? It's just the initial crazy expression that we started with. So let's substitute that in. So dy over dx is going to be x times square root of x squared plus 1 divided by x plus 1 to the 2/3 power times 1 over x plus 1 over x squared plus 1 minus 2 by 3 times 1 over x plus 1. So here's a pro tip for all you guys who don't like the product rule and or the chain rule, not the chain rule but the quotient rule. All you guys that do not like the product rule and the quotient rule, here's a pro tip. You can let whatever function you want to differentiate equal y, take the natural log on both sides like I did over here, and using the log properties, multiplication gets converted into addition, exponentiation gets converted into multiplication. So you scale down the severity of powers by introducing a natural log. So anytime you see a crazy product slash quotient which has many absurd powers, like half in this case and 2 by 3, which using the regular product rule and the quotient rule will make it way harder and way worse to calculate, you can just take the natural log on both sides, and then, as I said, multiplication gets converted into addition, exponentiation becomes multiplication by that power, and then differentiation becomes way easier. But the only catch is you have to use your implicit differentiation, because you'll have a natural log of y on the other side of the equation. So just keep that into mind, and then just don't forget to substitute back your y, because y is something that you introduced. So substitute y like this. So now let's do a last one. So they're telling us to differentiate this expression, the square root of x minus 1 times x minus 2 divided by x minus 3 times x minus 4 times x minus 5. And all this is under a big square root. Now look at this, there is a weird power of the square root, or the raised to a half power, and we have crazy products and also a quotient, right? So let's let this equal to y, and now, as I said, because this is a last example of reducing effort using logs, we get to take the log on both sides. You might have already guessed that. So we have the square root of x minus 1 times x minus 2 divided by x minus 3 times x minus 4 times x minus 5. So let's differentiate. Before differentiation, actually, we can just apply some properties. natural log of y being equal to, we can bring the multiply by the power, half of the natural log of, well, we can split these up, multiplications become additions, so x plus 1, still have the half, plus half of natural log of x minus 2, minus, because now we are in the denominator, half of the natural log of x minus 3, minus half, still in the denominator, natural log of x minus 4, minus half of the natural log of x minus 5. Now, great time to differentiate with respect to x. We get 1 over y times dy over dx is equal to half times 1 over x plus 1 plus half times 1 over x minus 2. Well, this is a minus 1, sorry about that. Minus here too. Minus half times 1 over x minus 3 minus half times 1 over x minus 4 minus half times 1 over x minus 5. And I would recommend not taking the LCM of these crazy sums, because it's really bad. And dy over dx is just y times this mess. So y times this mess. I don't want to write. I don't want to substitute y. I don't want to write this mess again. It's a lot of effort. Trust me. So I hope you enjoyed this video, guys. Please like, share, and subscribe to my channel. Recommend me to your friends, mathophiles, number files that you know, or people who actually want to learn calculus sitting at home. And stay home, stay safe. Have a nice day. Peace out.